perfect black body and its spectrum. A perfect black body is one which absorbs completely the radiations of all wavelengths falling on it. Hence, a perfectly black body neither reflects nor transmits any radiation. It is for the same reason that it appears black, irrespective of the wavelength of incident radiation. When a perfectly black body is heated to a suitable high temperature, it emits radiations of all possible wavelengths. This radiation is called black body radiation. It is not possible to attain a perfectly black body. A surface coated with lamp black or platinum black is an example of a perfect black body. Such a surface absorbs 96% to 98% of the incident radiation. For accurate experiment work, the black body designed by Ferri is generally used. Ferri's black body is a closed double-walled hollow sphere having a small opening O and a conical projection P opposite to the opening. The projection prevents direct reflection of any radiation. It is painted black from inside. Radiation entering the opening suffers multiple reflections at the inner walls. After a few reflections, almost the entire radiation gets absorbed. When the body is heated, it becomes a source of thermal radiation. The radiation from a constant temperature enclosure depends only on the temperature of the enclosure. It does not depend on the nature of the substance. Note: radiation falling on the hole is completely absorbed. When the sphere is heated, black body radiation emerges from the hole. So it is the hole which is to be regarded as a black body, and not the total enclosure. Distribution of energy in the spectrum of a black body. In 1899, Lummer and Pringsheim experimentally studied the distribution of energy in the spectrum of black body radiation at different temperatures. An electrically heated enclosure with a hole was used as a source of black body radiation. The radiation was passed through a slit S and made to fall on a concave reflector C1. The radiation was then made to fall on a rock salt or fluoride or fluorspar prism. The prism was placed on the turntable of a spectrometer. It was found that, like ordinary light, the thermal radiation got dispersed into its component wavelengths when passed through fluorspar prism. Lummer and Pringsheim used concave reflector to focus the radiations on a sensitive thermometer or bolometer. They connected a galvanometer G in series with the bolometer. The deflection of the galvanometer gave the intensity of radiation incident on the bolometer. Lummer and Pringsheim measured the intensity of radiation corresponding to different wavelengths. Heating the body to different temperatures, they made a number of observations. The results of the experiment were plotted graphically as shown here. Each curve represents the variation of monochromatic emittance E gamma with wavelength lambda. Let us now analyze the spectrum. We observe that no curve enters the visible region. This is due to the fact that the fluorspar prism absorbs the radiation corresponding to the wavelengths of the visible region. The distribution of energy among the different wavelengths of the spectrum of black body radiation is not uniform. At a given temperature, the energy initially increases with wavelength, becomes maximum corresponding to a particular wavelength lambda m, and then it begins to decrease. With an increase in the temperature of the black body, the maxima of the curves shift towards shorter wavelengths. In other words, lambda m decreases with an increase in temperature.
You've certainly seen infrared goggles before, and maybe you've seen this scene in Predator where Arnold covers himself in mud to mask his